Okay, yeah. So today I want to talk to you about model and paper development and research. So specifically going into the details of how to build good research models, how to set up a good research work, and what makes probably publication successful and more increase the chances of getting accepted. My name is Professor Kalman Graffi. I'm currently Professor for Networks, Communication Systems, and Cybersecurity at the University of Applied Sciences in Bingen in Germany. Short background to myself so that you have some kind of context. So I have a diplomas or similar to master's degrees in mathematics and in computer science, PhD degree in electrical engineering. Have been also for some time professor in Düsseldorf for technology of social networks, where I had the pleasure to meet Newton. And basically my last position in industry was that I was a principal scientist and leader of a competence group for reliable systems and software at the Honda Research Institute in Europe. Some further words on my background. So probably adds more context. I have roughly 100 publications in IEEE ACM conferences and journals. I didn't really count the reviews, but more than 200, 300 reviews, and from that some kind of experience of what makes research work and the presentation of research work more successful, supervising nearly 200 students, and being member of several young academies, national and international ones. My field of research domain is more in the domain of secure network systems, such as peer-to-peer systems, secure peer-to-peer systems, secure mobile networks, mobile ad hoc networks, opportunistic networks, swarm networks, but also secure distributed social networks, or a little bit newer, since a few years, also secure and confidential computing. So how can industries compute on customer data without having access to the data? Okay, so as what I want to talk to you about is basically to summarize my experiences on developing a research topic and modeling in science. So I want to focus basically on the best practices in how to build a good research topic, how to structure the work, how to build a model for the research work, and basically how to add what my findings are, what makes a paper successful, and what are the drawbacks, and also what are reasons to reject the paper when I read them. So to hopefully give some guidance and some experiences and insights. So I structured my presentation as following. First, I will talk about the problem statement. So basically on the right side, you see how a typical paper is structured with title, author, abstracts, keywords. Let's put that aside. And then basically an introduction listing the problem statement, motivating which work is done, and really describing what exactly is addressed. This will be one essential element. Then the description of the solution. There we'll talk about how to evaluate a solution, so discussing of results. And there are 2 points where related work can be discussed. I will discuss it a little bit later in this presentation. And finally, to add the introduction and conclusion. And also when I supervise the thesis, the many theses I had, I find this kind of approach and order of events is quite reasonable, as it has some benefits, especially focusing first on the problem statement and solution, where you have really some concrete next steps rather than discussing related work. Okay, let's dig into the problems and then the elements that we look into, and the element of modeling, let's say, in this context. So I looked up some definitions of modeling, and it describes the activity of using mathematical models, or in other words, simple descriptions of a system or process to do something with it, either to calculations, predictions, or whatever. Another definition tells that it's the representation of mathematical of something that can be a process, concept, operation, or system, some implementation. So it takes basically the essence of what we describe and gets rid of all of the unnecessary elements of it and keeps the core. So it helps us by modeling, by really focusing on the essence of the system, to have the focus on it and to really see what takes influence on the system, what are the key elements of the system, and also what can be left out, so to not obstruct the view on the core elements. Also, it helps us to define the assumptions and the environment we are operating in. So this specifically describes that if we just use common day language, basically, then there might be some ambiguities, but by modeling and by the detailed and concise description of what we actually talk about, ideally in mathematical formulas, then we can pinpoint what exactly we talk about and what not. Basically, then with this exact description, it is also easier to address the problem with a dedicated solution, because we can work out what we are talking about and what is needed in order to solve a given problem, and then also later to evaluate it. I will go a little bit more in details on this, but a little bit furthermore background on the topic. So basically, if we talk about various problems, I mean, and problem fields in the domain of computer science, there are various lists to list the research fields. Here, some few ones that I've been prominently working on. So computer systems and networks, security and privacy, artificial intelligence and machine learning. But of course, there are also other fields such as databases and so on. Operating systems, software development, you know the categories. In contrast to let's say models from biology or natural sciences, where we explore and observe the world, in computer science it's more constructive and generative approach. So the models that we talk about here are basically in the focus of developing something, developing a system that can do specific things in a very abstract format. Basically, it's not an observation of what is out there in nature. It is not an observation of people and their interactions. It's proposing some mechanism, some solution, some system that has specific properties. So this development aspect is very important here. And therefore also how we address it and what kind of elements are belonging to this model are slightly different than, let's say, in natural sciences or in sociology or psychology. So to give some more concrete examples, what kind of problem statement we talk about. Concrete examples, for example, is a routing protocol, let's say. So if you're familiar with networks where we have several nodes that are connected to each other, a classical problem is that we have given a graph of currently connected nodes, and they generate messages that need to be forwarded and routed to a destination node. Very classical problem in networking domain. And then some of the problems are how to make decisions to which nodes to forward incoming messages. Another example, more from the cybersecurity field, is if we have given a set of data items with specific access policies, how can we enforce these access policies? How can we make sure that no other entity can access the data that they are not eligible to? So what I want to boil down this discussion on the problem statement is basically that in order to build a research project and research approach, we have to start at clearly identifying the problem that we are talking about. And in the field of computer science, it's really a generative approach, so where we look into what kind of open questions do we have and how do we address it. And the first step for that is to be exact in what kind of problem we are talking about. Basically, it consists of three steps that we should look into to explicitly define what is given. So if you consider it as kind of mathematical equation or task to solve, you have to give an even play field for all participants, all researchers that want to address the same problem. So you have to specify what kind of elements you provide as assumed for them to be used. So you have to define first what is given, what available functions can be used, what actors are involved, so users, attackers, services to be used, and what further assumptions you make, so especially on capabilities and properties of these functions. Just to give an example, again, from the networking field, where it's quite well standardized. So if we, for example, want to operate in the domain of the transmission layer, the transport layer, it is clearly specified what the routing layer below, so the IP layer, offers, what we can do, and it is clearly specified what we want to have as an outcome of this layer. So if you clearly define what assumptions you make, other researchers can also join in to try to provide solutions for this domain. Then the second point is to clearly describe the desired outcome. So basically, in the first step, it is defined what is given, what kind of functionalities we can use from the bottom layer. And with the second, it is defined what kind of functionality we aim to provide to other participants later that use this functionality that we talk about. So you clearly have to define what do you accept as a solution, what kind of criteria should it fulfill, both in terms of functionality and quality. And as a last point, to explain the difficulties. So why is it hard? What kind of challenges do emerge? Why is it not obviously solvable? And also what kind of decision points there are. So what kind of freedoms do you have to make a decision how to solve this problem? Sometimes in the network layering, this might be easier, but in let's say distributed software stacks, where various software elements work together and rely on the services of the APIs of other services, it is more hidden. But in general, you always have to, a researcher always has to describe very well what kind of assumptions we have, what we aim at, and why it's difficult. To give you another example that I want to use as an example throughout the presentation, it's about opportunistic networking, to showcase you how this could be done and what, why the steps are relevant. So let us assume we have some kind of network that we envision. So we have nodes, communicating parties that have identifiers. So you see the picture down here below, they have some kind of numbers. They have a buffer for messages where they can put messages in. It is limited in the size, and they walk around. So this is everything we need to know with regard to the nodes. And of course that they can communicate with other nodes in a specific communication range. What do they do? So what is the activity that we envision? So they send messages destined to specific other node IDs. So here in the bottom, you see that the source node is sending a message to the destination node. And because they walk around, they have opportunistically some encounters with other nodes. So they try to carry the message as long as they can. And once they meet some other node, then they can consider the forward messages they have from the buffer to the other node. Also, this is describing the properties of the nodes. And finally, some of the properties of the messages, they contain information on source and destination addresses and payload, some further metadata such as message size and time to live, so a clear time stamp when the message has to be deleted and is not relevant anymore. And for every node further contains information on when did the message arrive at the node, how far has it already traveled to the hop count, how far has it traveled from the source node, and how often the specific node we are currently in has forwarded this single message. And basically, this is describing what is given. And what we are now looking for is to find a solution that allows us to deliver messages as quickly as possible to the destination. So why is it difficult? So basically, you don't have a connected network. You cannot take influence on where the nodes walk. So you have to rely on random encounters and opportunity of the nodes to transfer messages. Flooding is not really working to get your messages to the destination, because that would fill the buffers too quickly. And you have to take decisions which message to send to which node when you meet them. Basically, if there are several nodes to whom to connect, if there are several messages in the buffer, which one to send, if your buffer is full, which message to drop, then you can further decide what kind of further information you want to carry, you want to maintain in order to support your routing protocol, and follow-up questions, how to implement it on smartphones, and further questions. But here you can see basically it describes what is given, that is very essential, and the desired outcome that gives basically a play field for researchers to come up with competing results and competing proposals, how to solve this problem. How can we make the decisions in a way that we maximize basically the number of messages arriving at the destination in the shortest time? And by having this equal playing field for every kind of researcher, competing results can emerge, and competing solutions can basically have a look which of them is better. And this is then basically what research is. Okay, and let's say what kind of issues can emerge here. When I've been reading papers and reviewing them, then I encountered sometimes problems that led me to reject the paper or to give some strong feedback. So let's see what kind of issues can arise. So first of all, if there's no definition of what is given, that sometimes happen if the author just goes ahead and presents his solution without really motivating what it is for and can it be ever used. If there's no motivation, this is really some kind of problem for the paper, because the reader is not motivated to read it or convinced that it should be discussed about at all. Also, what I sometimes observed is an incomplete definition of assumptions. So basically, there's in the beginning some set of assumptions, and at the end, when the solution is presented, how the author tries to solve the problem, then he comes up with out of the box new assumption that helps him to solve the problem. So this is then the reviewer feels cheated, and that seems like an unexplained trick only to support the solution. So all the assumptions basically that are made and that are given as a starting pack for researchers operating in this field should be described in the beginning of the paper to make it very clear what we operate in. And there should be no surprises in the follow-up of the paper. But I also sometimes saw that the assumptions is distributed or scattered across the paper. So a little bit in the beginning, then a little bit during the discussion of related work, then some assumptions are also further introduced in the various steps of the solution that are presented. And this is also problematic, as the reader cannot identify at one single spot what the problem is, problem statement is, what kind of challenges to be tackled. but has to keep the history of what, I mean, has to really check and very diligently look for all the details and hidden information of what the paper actually addresses. So all assumptions, all problem related descriptions should be in the beginning so that it's very clear what the paper is about. In the same context, if there's no desired outcome sketch, that I also saw several times, it's just, let's say a problem is described, but there's no criteria what a solution might be. And that typically leads to, I always get the feeling that this is some kind of description of an open source project that is continuously developed and grows and grows and grows. So if there's no hard limit on what's the acceptance expected outcome and what is the aimed at outcome, then basically the paper is never ending and the development is never ending. So it has to be precisely defined what an acceptance criteria is for a solution, so that various researchers can compete for a good solution in that domain. What I also saw several times is that if difficult is not explained, combined with they are obvious, then the reviewer is sometimes not willing to think so far ahead to identify what the problem is, I mean, what the challenges are, why it is difficult, why it is a relevant problem. So it leaves the interpretation of the relevancy of the paper to the reviewer, who's not so often interested in really putting too much effort in it. So by not describing the difficulties, actually the paper loses in quality as the reviewer doesn't see the difficulty in the problem so strictly. So it's always recommended to describe the problem as clear and as well as the difficulties and as clear as possible. But I also saw several times when there's no problem, just a solution presented. So basically it's very similar. So the motivation is we implemented X as no one has done it before. And we added this feature and we added that feature, and now it can do this and that. And that, again, is not really a research paper. It's more like an open source project that is continuously developed and does not really help anyone reading it, because it's not specified for which problem, for which demand this is formulated. So basically the summary on the problem statement is that it should be as exhaustive and at the same time concise as possible. So really describing what the demand is. So what is given? What are the acceptance criteria for a solution? So when do we call an approach a solution for this? And why is it difficult? And once we have this, then we can have a look how to describe our solution for it. So I will jump over the part of related work in this step, so I will pick it up later. So now let's say we have defined the problem statement, what we are operating on, for what we are looking for a solution, and when we can say that we have a solution based on acceptance criteria. So basically the solution is embedded in the layers or the lists between what functionality is given. So this is what we can base our solution upon. Then we have specified what is desired, so what is the necessary outcome to call it a solution. And we have specified constraints of the environment. So for example, the resource consumption is limited to a specific factor, or it must be a distributed solution, or there's no trust in specific elements in the system, so that needs to be accounted for. And once we have specified basically what is given, what is desired, and what kind of constraints we face, then in that element we can use functionality from what is given in order to provide what is desired and provide our solution. And basically, how we use what is given for us to provide the solution is defined through a set of design decisions. Typically, if the problem is hard and the solution is not obvious and there are different options how this can be solved, so we have to see where are decisions to be made. So to pick up the routing problem in opportunistic networks again, as we had the example, the nodes walk around, they have a buffer, and let's say they meet some other nodes and they have to decide which message to forward. So they have a buffer full of messages, let's say 100 messages, and now they have to select which of the messages to select. So the design decision is to send a message or not. Then the next design decision is if to send a message based on what information, for example, based on the replication count or hop count, based on the speed or direction of the encountered nodes, based on the interaction history. So different options, what we can combine in a set of decisions that form our solution. Of course, there's sometimes even more information or more functionality that we can use, such as cryptography or other technologies that our solutions can be based on. Just want to put it in this context. But basically, by making a set of decisions, we come to one dedicated solution. And I want to discuss a little bit about the ambivalence of one solution in comparison to a set of solutions or parameter studies. So basically, by a set of choices that we have and that we make, we come to one specific solution. But if we are able to vary one or several parameters, then we already extend the solution space that we are operating in. So so if we consider, for example, having for one of these choices the freedom to parameterize results or to select from a known and limited set of options, then of course we could also test all alternatives in that specific region for that specific design decision in order to identify some kind of best choice. Again, let's have an example. So now we are again in this opportunistic network domain, and we get the message by some random encounter, and our buffer is full. So we have to select, first of all, which message to drop. So this is our buffer. The messages have this kind of meta information. And if our buffer is full, then we have to select one based on the information we have to drop. And if we have to send messages, then basically based on the same information that we have here on the messages, we can decide whether to send a message or which one to send. And especially also here, if we apply different strategies, so let's say this is epidemic routing, so we forward the message every time, then we get some kind of flooding. If we first prioritize to increase the hop count, that means that the message first has to travel quite far from the source node and only then to replicate in the breadth, then we get this kind of tree. Or if we prioritize first the replication counter to first spread it into the neighboring nodes, but then only very few forwarded on. So we can take influence basically based on our decisions, we define our solution. Again, so let's see what kind of challenges do we face here. And again, summarizing my kind of experiences from the various papers I've written and reviewed. First of all, what is not to be done is to come up with some hidden assumptions or deus ex machina. That means if in the beginning there was some kind of problem statement defined with what is given, what we assume, and what the acceptance criteria for a solution is, then it is unfair to change it during the proposal of the solutions. I saw this several times, where basically assumptions were not sufficiently stated in the beginning, and only in order to give the own solution an advantage, the authors came up with some kind of support and new assumption at the solution section. So if you would introduce some kind of shortcut in the network, you know, a small example, that would be some kind of feels like cheating. Another problem that might occur is vague descriptions. So if the wording, the visualization, the description of how you solve the problem is vague, leaves the design decisions open, does not specify to the full how you operate with what is given and how to reach the desired goal, then there are holes basically in the solution, and the reviewer is not interested in trying to figure out himself how to resolve them. So if it's hard to follow how the solution is, if it's not well written, if there are parts unexplained, then most probably the papers will be rejected. So always be precise, use models, formulas, figures, models in the sense of mathematical models, describing as precisely as possible what you do, give algorithms. Then it is better to give them more details so that it's understandable than to leave out any relevant parts that is required to be understood. Okay, another issue that I sometimes also saw is the lack of motivation for design choices. So if the solution is presented, and let's say the author has different options how to build his solution system, let's say the routing protocol. It could be a reactive or proactive routing protocol. It can be based on one of the 5 metrics, metadata of the messages in the selection I presented before. And if it's not motivated why a specific design choice has been made, then it looks quite random. So it's not really helpful and will be questioned by the reviewer. It's not the KO criterion, it's not too hard. But if it accumulates and it is unclear why specific design decisions have been made, then the interpretation and the mood of the reviewer basically changes to the bad. What I also saw several times, and it's really annoying for a reviewer, if the description of the solution is scattered, so distributed across the paper, where you at, I don't know, page 2, describe how you do the first part of the solution, then page 4, the second part, then you have somewhere later short introduction of some modification of the solution. So if the review has to keep track of where the solution is described in detail, and in order to understand how the big picture looks like, how the complete picture looks like, then that effort will not be done. So it is also unclear whether essential details are missed, because it's then left up to the reviewer to identify what is relevant or not. And that often leads to a request to rewrite that parts and to put it in one spot in a full description of what the solution is. Also, what I saw several times is people writing the story of their lifetime. So where they more follow the timeline, how they developed the solution. First they did steps 1 and 2, then 5, then they figured out that step 4 should be done before, then they revised parts of the solution, and they introduced a new step 6, and then they changed the first part again. And as a reader, you have to keep track of what is the final state, and this is really annoying. So it's first, the presentation of the results of the solution should be what is the final state of the solution, so that this can be taken as a reference later in the evaluation. And after that, there can be alternative choices discussed and whatever happened, but there has to be a concise description of the final solution, basically in the beginning of the solution part, in order to help the reader to understand new ideas and all the details and the history are not so relevant. But problems can also occur that are typically solved when by student thesis, so master or bachelor thesis, if they write to themselves or very close peers who are already very familiar with the topic. And by that, they minimize the descriptions and the details and the motivations. So this is really a difficult style in that sense. So the paper should always aim to include the reader, assuming this is a regular computer scientist, let's say, without being too close to the field that we are describing. And especially in the domain of cybersecurity papers, what I've observed as review often and what led to rejections is to have an attacker model that ignores the solution. So often I saw that, for example, some kind of reputation model is introduced that marks malicious behavior and communicates it to the other nodes in the surrounding. And somehow the good nodes use that system, and the malicious nodes, they act as if they would not know that it's available and that it's in place. So you have also, even if you introduce some kind of cybersecurity solutions, assume that the attacker knows of that systems, and sometimes, especially with reputation systems, it's easier to misuse them, and sometimes the solution is a bigger problem than the initial problem it was. Okay, so to summarize, again, have a very clear description of what the problem statement is and stick to it. And then for the solution, make clear what the design decisions are. And if you make the decisions, why they have been done, motivate it well and put it in one place. Coming to the evaluation, what to look into, what to look for when writing a proper evaluation of a solution. Up to now, we have the problem statement and solution. And to be honest, quite in the beginning, there should be the discussion of what are the metrics by which we evaluate different solutions in terms of their quality. So what is a metric? I mean, it's a set of numbers that give information about particular processes or activities. So it describes a quality property. And it is, so for example, in the networking domain for the opportunistic networks, we have that would be delivery ratio, what ratio of messages can be delivered, or delay, or overhead, how many copies of the same message do we have in the network. That would be an example. But they always require a very proper definition that shows how they are measured and why they are relevant, so that the reader, the reviewer, really sees that these are the main relevant metrics, how to obtain them, and why this is reasonable to consider them as a valid candidate to combine, to compare various solutions to each other. Of course, there can be also some kind of further internal metrics that are not really displaying the quality of the system, but support the analysis of what's happening underneath. But at least after presenting the solution, there needs to be a proper definition of the metrics that are used to evaluate the quality of the solution. Typically, then you have a set of metrics. So in this case, let's say we have 3: delivery ratio, delay, and overhead. And there has to be some decision and a motivation, which of these metrics, what is the properties, or which is the most important one, and how is the order of metrics. So in this case, for networking, the delivery ratio is highest order, highest relevancy. So it's more important that the messages are delivered than that they are delivered quickly, or that it's cost effective. Of course, based on the use case, there can be some differences in the priorities, but typically that should be specified in the evaluation and motivated why the specific selection has been made and why these metrics are relevant and why this order and relevancy of metrics is discussed. Okay, and then basically describing the evaluation environment. So my experience is that papers without evaluations are, I mean, very hard to get accepted. So there has to be some methodology in the evaluation. I've personally participated in theoretical analysis, proof, simulation, or real-world tests. And it is really essential to allow the reader to understand what has been done in which environment, and in order to allow replicability so that somebody else can redo the same experiment. It's also required to be aware of the limitations, so to not overpromise in what the findings can be. So, for example, I saw in analysis that by having a specific model of what you describe and what you analyze and what you prove, it really only captures a part of the reality. It's not the full reality, and it's only limited, and therefore several aspects cannot really well proven or modeled, such as synchronous activities, errors, misbehavior, quite problematic. Simulation is a little bit better, so especially in the networking field. So if you simulate large networks, depends of course also how well your models are for user behavior, for network characteristics, and so on. But typically it offers you a scalable approach to thoroughly get insights of how the behavior of your solution is, and can expose some unexpected characteristics. So it's quite good to learn from. And real-world experiments have also their benefits, especially they are eventually required. So in order to validate that it really works, what has been built. But their challenges is typically they are limited in scale and what can be tested. It's very time and resource consumption. It requires high resources and then time efforts to do this, and more difficult to measure what happens, especially in distributed systems. Okay, coming to some example again. Let's assume we discussed this buffer management issues in opportunistic networks, where we have this mobile nodes, and they have some buffer that of a specific size, and the messages have specific characteristics. And we want to decide now on a buffer management strategy, both to decide which message to forward if we meet some other node, and which message to drop if the buffer is full. So this is the problem that we are facing. And one example solution, very simple one, is to, let's say, always send a message with the minimum number of replications. So that messages that have yet not been shared. And to drop the message with the minimum time to live, that would be anyway be dropped soon. That would be one simple solution. And if we evaluate it, so just an example, we used a simulator, opportunistic network environment. We specified the simulation time, which base routing protocol we used, what kind of movement patterns we considered, again, movement, what communication ranges we considered, and then several scenarios, how the composition, how many messages are generated, in which rate and which size. I don't want to go too much into detail on this specific research field, just for the methodology. And what to look for into when evaluating, basically that single results are not really interesting. So for example, if you know that the scenario 2 with specific message sizes and node speeds, we have a 88% delivery ratio, that's not too interesting. So it's more interesting if you have several runs and confidence levels that shows that in general this kind of quality is obtainable. So this should just visualize it. So please do not relate it to the networking point. It just shows how confidence levels are giving a stronger impact on the reader than having a single number. And also, if you can run parameter series to confirm or identify the selection of right parameters, design decisions, that is often of higher help. So here, for example, just to zoom in, so these are 11 times 11 combinations of drop policies and query forwarding policies, and we identified what is the overall best, let's say, parameter selection design decision to be taken in specific scenarios, but only limited to that scenarios. So it's better to be present more and in more detail, of course, and for higher confidence level. But at least if the resources and time is limited, then of course it's better to focus on a clear message, on a well-validated confirmation of that message, rather than making too many claims that are not supported by the numbers. And be fair in the discussions, especially when I see a paper that shows that the solution is flawless and better than any solution before and it has no issues. This is always a red flag that there's some problems. So always discuss the limitations also of your solution. So as a reviewer, again, to put on my reviewer hat, when the evaluation setup is unclear, that it's typically signaling that something is hidden. If I don't know how many nodes have been simulated, on which tool, what network model, or what kind of base assumptions have there been, what kind of design decisions made, or for the evaluation, what kind of constraints have been set, that's strange. And so of course not the readers, they're not able to reproduce the results. Also, if some of the metrics are selected in a strange way, if one of the metrics are highlighted as most important one, which I do not agree to, then it seems like it has been tuned to fit the solution. So the problem fits the solutions rather than the solution fits the problem. Also, what is sometimes questionable, if there's strange parameter selections. So let's say if you simulate the network and you simulate 991 nodes, why not 1000 or 2? Or, I mean, why not some clear numbers that are easier to reproduce? That might also hide some kind of shortcomings. Maybe 9 nodes or a specific number of nodes were always failing that are not described in the solution. So ideally, always use magnitudes, exponents, powers of 10 or 2. That allows, at least in my domain, networks and distributed system, that is quite often used and allows for comparability of the solutions. So if somebody else runs with his solution similar numbers, then they typically also pick these network sizes or system sizes, and then it's easier to compare the results. If there's only one simulation run or 2, it might hide, or might be an outlier, or might hide that these were only the lucky cases that were good. Sometimes it's understandable, especially if it's real world experiments, then it's typically just one setup. But that might also signal some kind of problem. So better to have repetitions and to evaluate several times and to compute the confidence levels in order to support the claim that is made. If in case of there are no results discussed, so let's say only the numbers are given in tables or only the strengths are discussed, this is problematic, as it leaves the interpretation of the shortcomings to the reviewer. And if the reviewer finds undiscussed weaknesses, especially some holes, some problems, he assumes that there's more. So better to proactively come up with the limitations that you see, put it in context, that in specific scenarios your solution works well, and others it doesn't work well, but you propose to use it only in the good scenarios. To be transparent where it works well and where you have where there are limitations, and this is giving more confidence to the quality of the paper than to have a solution that is everywhere good. Something done on the presentation, especially on how to write and what kind of figures to put in. So this is more on the form. If I hardly had seen any kind of paper written in Word that looks good or professional, and also please avoid to use bitmaps for figures. They are hard to read. you cannot zoom in, and that gives an impression of a low effort paper if the presentation is not polished. My recommendation, but just a recommendation, of course, just, I mean, LaTeX is free to use. Scalable vector graphics are easy to integrate there, and they are infinitely zoomable. So it's always keeping the polished look. Also, some word on the alignment of figures. I recommend to put it on top or bottom of the page consistently, not in the middle of text, as sometimes this is really hindering the reading and does not support the professional look of the paper. Okay. Sorry, okay. Just I think 2 slides or so more. Some words on related work and why I put it on 2 different places. So you can put related work discussions basically at the beginning, so directly after the discussion of the problem statement, or at the end. If you put it in the beginning, typically it is useful if you identify the niche with no solution or very few solutions yet. So here you see an example from one of my papers, which puts various related work in some kind of classification and basically points out that there's a gap in which the new solution will be proposed. This is reasonable, and it's always good to have in that context some kind of classification, but it typically is useful in a domain, in a case where there are not so many related works really in that class that your solution falls in. So it should be a niche that is quite unpopular. The second point is to put it at the end. That, I mean, I don't have really a strong recommendation on this. Putting it at the end might help to point out design and quality differences to existing solutions, especially if you want to compare your work to the related work in terms of how you have differences to it, or how the evaluation results differ to it. Then of course it would be good to have first presented your result, your solution and the evaluation results. And therefore, if you need that knowledge first, then it's sometimes better to put it at the end, and then you can really compare related work with your solution and put it in context and refer to text that you already talked about. But in general, it's always recommended to be fair in the discussion, point out differences and unused potential. Assume that the author of the related work is the reviewer, and give credit where credit is due. So all solutions have some kind of niche where they are good, and it just probably is the case what scenario we're looking at. Again, some thoughts on this. So if you don't have a discussion of related work, that's quite implausible that this is a very new, fresh research domain that nobody looked into. So that typically signals that there's not sufficient diligence have been put in understanding what the current state of art is. And this is not extending state of art, this is more reproducing it. Citing old papers, very similar. Your paper is living in the past. So that also means you are not extending the state of the art, the current knowledge, but you are reproducing it. It's also not. So you should always keep track of the current state of the art, the current papers, and put your paper in context to it. Bashing related works, of course, not good, because that will set the negative tone also for reviewing your paper. And what do you do if there's no difference at all to related work? So do you find a solution which exactly matches yours? That should, of course, not really happen. If it happens, then at least you can propose to have a new set of evaluations for it. I'm not really sure how much it adds to research, but that's good. And if the difference is only small, then you might call it an extension, evaluate different scenarios again. But ideally, you should have a new idea what you follow up. Okay, final part, let's say. So once, I also recommend to my students and PhD students, and then whenever I write papers to follow this order, basically first the problem statement, be very clear what you aim for, the solution. There you cannot change anything. This is fixed and you have to describe it in a proper way. Evaluation to be done next, and the introduction and the conclusion basically at the end. So what it is used for? it motivates the problem and its relevancy, so that it really, the reader has an incentive to read it, so that the reader learns why is it relevant and what will I learn, and only with this information the reader will pick up this paper to work through. And it's also essential not just to motivate problem and relevancy, but also to list the contributions of the paper. So you really have to tell the reviewer what are the highlights, the main points that you bring in the paper. You must not leave it to the reviewer to interpret and to identify it for himself, because it's obvious, because that would leave the reviewers less interested to read. For the conclusion, basically to repeat the problem statement, rough idea of solution, and highlights and main results of the evaluation. Basically, that should be sufficient to read in order to understand the full outcome of your paper. So sometimes also the reviewers read only first read introduction and conclusion. Is it worth to read? Is anything new a new idea to expect? And any strong improvement in comparison to related work, that should be the goal. Just an example for my conclusion: problem statement is described, approach is described, and the evaluation and what it means for the future in this domain, and then limitations and future work, just to give you an example. Okay, final word. So this is also the last slide. So consider the audience, so to be really sure for whom do you write, and address them and keep them in mind that they should be interested, they should be motivated to keep reading. Focus on the impression you make. So professional look of paper is essential, because it's sadly the form is sometimes more important than the content. So great ideas in bad shapes are rejected, but simple ideas well presented are likely to be accepted. So this is sometimes my observation. So it's very important that you give a good impression. Control the narrative. So don't leave it to the reviewer to interpret what might be good in your paper. Tell him what they see, tell him why it's good, tell them why it's relevant, and keep the control on the narrative. Don't leave it to the reviewer to have the work to find out why your paper is good. Also on the psychology of the reviewer, so typically my observation is that decisions are very quickly made on whether accept or reject, and only after that the reasons are looked for. So the first impression is very important, therefore also the form must be very in shape. The first impression is very critical. Minimize the work of the reviewer. Tell what you do, where to find it, the findings, then the conclusions, and really don't leave it to the reviewer to make up and to find out why your paper is interesting. You have to summarize it to make it easier to read, easier to consume. And as a final point, probably my experience, there's no rejected paper, only papers that have not been resubmitted. Of course, there are also some limits to this, but typically, if it's not accepted at the first try to find a conference with a slightly better acceptance rate and try it there. After 1-2 tries, that should work. Okay, thanks for your interest. I hope that was somehow helpful and or interesting. I hope I matched the topic that you were looking for, and I'm happy to answer your questions. Thank you very much.